Hello, welcome to video 19 in the lecture Advanced Mathematic Modeling. Today I want to first show you some not tricks, ways to count stuff, because when you want to solve the exercises and you have some applications, very often you have to count events. In the end we want to get to probabilities. We always need to count the size of the sets of the associated events, and sometimes this is simple, but sometimes counting can be really tricky if you're not careful. And I want to give you here the formula to two important ways to count stuff. So let's do this. And the first, if you have permutations, how to count the number of permutations. So we want to know count number of permutations of R distinguishable objects out of a set of n objects. So like counting is always a bit tricky if you have many objects, and then you want to select some of them, and you want to know all kind of possibilities. And with the permutations, this goes like this. So you have R objects, so you have so you take the first. So this, if you have like you want to have R of them, you have n objects. So the first can be, you have n possibilities, so you have n. Yeah, but then you have chosen this one of the n objects already. Then you have n minus 1 objects left. So the second second element of R has only n minus 1 possibilities left, and then you go on until the rth object is chosen, and then you have here for the last, you have n minus R plus 1 possibilities. Yeah? So you have this product of n times minus 1, and so on and so forth. And this is more easily usually if we write this with the faculty. So n faculty over n minus R faculty, and we of course always assume that R must be smaller than 1, otherwise we cannot choose R objects out of the calculate the permutations of R objects out of the n. So, and then when you count things, you usually get to this faculty things. Yeah, so that's for this. And the other thing what we need is combinations. So now we want to count the number of ways that we can choose R things or R objects from the n, and meaning we take no account of order. in the permutation, the order was very important, so we first have to say what's the first, the second, and so on, because with every choice then we have less choices left. With the combinations we don't care for the order, and then for so we obtain something. We have again this here, n faculty divided by this n minus r faculty, but now since the order is not important anymore, we must multiply this here by n faculty, and this combination, this appears so often, this has this certain symbol n over r, the binomial coefficient. Again, r smaller than n. So that's, you could also say that's the definition for the binomial coefficient, but maybe this reasoning here was a bit too short, too fast for you, that we divide here by r faculty. So maybe we can make a proof, short proof, that this is really the result. And so we want to choose r things. So now let's mark first one special thing. Mark one of these, one special of these are things. We mark this, and now either we include this in our combination, let's write already here, down here, n over r. So either we include this, and then this means we have to choose still r minus 1 things out of the remaining n minus 1. So we have marked this is included, and then we have still to find a way how to choose the other remaining r minus 1 things out of n minus 1. So this is then here n minus 1 over r minus 1. But we have forgot something, or it could have been that this chosen thing is not in our combination, so we exclude this. And then we need to choose still r things out of n minus 1. Then we have here n minus 1 and r. And so we get this nice recurrence relation of binomial coefficients here. And so you could also say that could be a definition of binomial coefficients, and you can show this leads exactly to this formula. And maybe, but I assume also that you have seen this somewhere. So when you start n over 0, this is 1, and then you can make this construction with the Pascal triangle. For when you use this recurrence relation, so you start with n over 0, that's 1, and now so we make here a list of all possible outcomes, of all possibilities of n over r, and here we go down with n. So this was n equals 0. Now we have n equal 1, then either r is 0 or r is 1. So in this direction we have r. So and then n over 1, n 0 over 0 is no 1. No, let's see here, this one. Oh, let's first go one more, then it gets more clear. So we want to know here in the second row we have this here. So you want to know, for example, what is n over 1 over 1. So this is 0 over 1 plus 0 over 0. So every value is given as the sum of the two values here above. And then if you always have the sum of two values above, 1 plus 2 is 3, 2 plus 1 is 3, and so on. And then we have here 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on and so forth. So in this table with this construction of the Pascal triangle, you can, which basically expresses this recurrence relation, we can reconstruct the binomial coefficients. So this was just maybe an outlook or excursion into ways to count things, and very often counting in this setting is always related to counting permutations or combinations. So now what did I promise you that we want to do? So what we wanted to do, we wanted to have again Bernoulli trials, but not as in the geometric distribution, wait for the waiting time, but instead now we want to have a fixed number of trials and want to know how many successes we have. So a different question. So we have the binomial distribution, we have a fixed number of Bernoulli trials, and this number is n Bernoulli trials, and we want to know what's the probability that we have k successes, so k out of n. And so that's now a random distribution for the random number k. And now you see, to have exactly k successes from all outcomes, this is now a combination. So how many combinations are there? That's n over k combinations. And then, so what's the probability? So we need now to have k times we have success, so k times we have the 1. This is the probability p to k. And then the other times we have 0. This probability 1 minus p to n minus k. And this k must be smaller than 1. So that's the binomial distribution, which incorporates here the binomial coefficients. So is this really a probability distribution? Is this really normalized? So let's calculate this. Let's calculate the sum of all this p of k. So now we have to sum from k equals 0 to n over k, p to k, and this 1 minus p we call it q, always q to n minus k. And so now what gives this sum? And there maybe you've seen the binomial theorem. You can write this as p plus q to power n, or here this is the binomial theorem. Or if you don't know this, like if you just factor this out, you work out this products, you write this n times and factor everything out, and you see order to powers of p and q, then you see all these terms appear with n over k times. Okay, p plus q, this is p plus 1 minus p, this is 1. So we see this is really normalized, the sum of all this. So it's really a probability distribution. So let's calculate the generating function, because now we want to know what's the standard deviation and variance of this distribution. So, and we directly use the generating function. Of course, we now could also try to solve moments from this. But now imagine yourself, now you would have to calculate expectation values with these binomial distributions. This could be really, really tricky. So, but the generating function we get very simple. So let's first write it like this. So we sum here P of r times s to power r, and we sum from r equals 0 to infinity. Now I call it my variable over which I sum r, so that I don't distinguish here with the k. So we have to calculate this expectation value. Now for this p we take in, we put in our distribution, which is n over r times p to r q to n minus r. R goes from 0 to infinity, and times s to power r, and now basically we can use here this binomial theorem again. So when we want to solve this, so we could directly see that we can write this as q times p to s. You see p and s can be put together. This is q plus ps to power n. If we just use the binomial theorem for this again here. And this is the generating function of s. But, this is the generating function of s. But we could have done it even more simple, because we know the generating function of the Bernoulli distribution. This is just q plus ps. Yeah? And now what we do here, this probability to have k successes, that's just the sum of k Bernoulli random variables. And the sum of k Bernoulli random variables, this we said, is just the product of the probabilities. So this means we have just to take, no, that's the product of the generating functions. Remember this here. The sum of random variables corresponds to the product, so the generating function of this is the product of the generating functions. So we just have to take the generating function of the Bernoulli distribution and multiply it n times with itself, and we directly are here. So we wouldn't even need to calculate this here. So this is one example where you can use these theorems for generating functions and like magic directly write down the generating function. And now once we have the generating function, we directly can calculate all our moments. So let's do this. So first, what's the expectation value? So we need to calculate the derivative at s equal 1. So now take the derivative of this function. This is n times q plus ps to power n minus 1 times p, and we take this at the position s equal 1, and this gives n times p to 1 to power n minus 1. This just is n times p. So that's the expected value of the binomial distribution. And let's calculate the variance of k. Now we use this formula, we need the second derivative of this here, and then we use our standard formula, the second derivative at 1 plus the first derivative at 1 minus the first derivative at 1 squared. You work this out and we get n times p times q. And so we obtain the variance and the expectation of the binomial distribution, and maybe K, P of K. Let's make a graph. So, I mean, probably you all know this, or if you plot this distribution, so you see it looks like a Gaussian. So the binomial distribution is like the discrete version of the Gaussian, just as the geometric distribution was the discrete version of the exponential, and the typical value here is n times p. And so I'm sorry if you have seen this binomial distribution already, but here for the exercise for the lecture, maybe you didn't see how to calculate properties of this with the generating function, and you see maybe here the power of using this tool. So we are getting out of time for today, but since we in the moment had elections in the US, let me make one last remark which might be very topical in the moment. So let's look at the US election in 2020. I mean, you were all aware of what happened here in the last weeks. And take a state like Georgia. So we have about 5 to the power 6, 5 million votes. And then we had Biden and Trump. And so that's in the moment as today the number of votes for Biden and Trump. So, I mean, it's still not finally sorted out, but I think 99% of votes have been counted. And when we take the difference, so we see the difference is rather small, something in the order of 10,000. And what was striking for me, how in such a state can we have such a close call? Let's assume you have an opinion formation process, some process which leads to a certain fraction voting for one person and the other for the other. So it should be some parameter, some result, but that it's exactly so fine-tuned to half-half, that sounds very striking for me. And now let's assume, of course, we can now regard this as a binomial process, or now we'll apply the binomial distribution. What would happen if every person would just throw a dice? So if every person would just throw a dice with p equal 0.5 and then q also 0.5 here, and then we ask what is the chance that we have exactly k equals this number of positive hits. And now then you would say, okay, this should be binomial distribution, and so okay, then of course on average it should be p is 1/2, so we should have exactly, every candidate should have exactly half the votes, but this is just the expectation. Of course we have a variance, and the variance or standard deviation, and the standard deviation we see here. So then what's the standard deviation? So let's first write the variance. Variance of k, this was n times p times q. So we had it's if both are 1/2, so this is 1/4. That's the variance of k. And so what's the standard deviation? The standard deviation of k, then this is square root of n divided by 2. So this means we have here n times k, we have a certain standard deviation, and the standard deviation goes with the n over 2. Now, but the standard deviation goes only in one direction. If we take here the delta, so we should expect for the delta, the difference, that this should be approximately 2 times the standard deviation. So, and 2 times this, so this difference should be of the order of square root of n. So that means if every person would throw a dice randomly, we would expect a deviation from the perfect 1 over a half-half outcome of the order of square root of n. Now what's the square root of, so what is this? So if you have 5 million people and you take square root of 5 to the power of 6, we get 2,200, something like this. So we see, okay, this difference that we have is maybe 5 times larger the deviation than if every person would just have thrown a dice randomly. And so you see here, so we can now judge this value, that this difference which came out in such a close state as Georgia, to the null model that people would have thrown dice randomly. And so it's a bit more. Of course, we don't know people. We know that people don't throw dice, and that's even more astonishing for me that we have such a close similarity to this, because every state is so heterogeneous. You know, in cities and countryside, we have very different proportions of the two parties. So, so that's even more striking in such a heterogeneous distribution. That is the state, and you have here different smaller counties, you know, and then you have some counties which are really Trump counties with high percentage of Trump and other of Biden. So it's really this heterogeneously distributed. Why on average this comes so close to this? Yeah? So yeah, just as a nice example of our binomial distribution. Thank you for today.